move directly to our next speaker, Professor Amanda Prorok, who will give us insights about multi-robot learning and how to leverage communication and explanations. Professor Amanda is an associate professor in the Department of Computer Science and Technology at Cambridge University and a fellow of Pembroke College. She is interested in multi-agent and multi-robot systems. Her mission is to develop methods to coordinate artificially intelligent agents to achieve common goals in shared physical and virtual spaces. Please join me welcoming Professor Amanda Prorok.
I'm delighted to be here today, and I very much hope that next time I will be able to visit in person. I'd love to come by and be there on site one day. So thank you very much for being here. Today I'm going to talk a little bit about our work on multi-robot learning and how we're looking into actually leveraging and learning communication policies able to help us develop decentralized policies. And at the very end, I'm going to be presenting a little bit of very new groundbreaking results we've produced on leveraging explanations to facilitate the learning problem. So as the introduction already kindly laid out very precisely, what we're interested in is thinking about how to endow autonomous agents with intelligence that enables them to cooperate towards common goals. And this general mission is really being driven by the idea that the next wave of computing is going to be about the convergence of ubiquitous compute, communication, and AI. And we really this is one of the key things, computing and AI and machine learning and also first principles approaches is coming together towards solving. So clearly we're really interested in multi-robot applications. This interest in terms of the application domain is really being driven by a number of commercially driven interests and industries where we're increasingly seeing a number of at least assisted devices or fully autonomous devices, even in some cases, leveraging more intelligent ways of coordinating and cooperating with each other. So very early in my work as an assistant professor in Cambridge, we decided we would go about and look into how exactly it is that cooperation and coordination can help. And we designed this experiment in my lab here composed of a bit more than a dozen miniature vehicles to show what happens when you don't coordinate and cooperate and what you can do when you do leverage cooperation and coordination. And so this experiment here shows you what happens in the case of non-cooperative vehicles. In this case, we're deploying vehicles with egocentric, human-like driving policies. And you can see that when we actually stop a car artificially on this miniature highway, creating an artificial bottleneck, we create this bottleneck scenario where the cars queue up and nothing really moves forward. And then we went ahead and designed by hand a policy that would allow the cars to cooperate with each other by simply communicating their incentives to each other and trying to optimize some higher order goals. So in this particular case, the higher order goal is to optimize throughput. And so the change is very subtle, but what you can see happening here is as the cars approach the bottleneck, let's see, just wait until the movie to wrap around again. So as the cars approach the bottleneck, they're actually communicating to nearby vehicles that they want to surpass this bottleneck. And the cars on the outer lane are just ever so slightly slowing down to make space for the cars on the inner lane to come out into the outer lane and overtake the stopped vehicle. So the change here is very, very subtle, but the cooperative aspect here is strong, and so strong that it helps to really increase the throughput by 35% in this miniature highway scenario. So the point I'm trying to make here is that it's intuitive and it's clear to us, at least, that cooperation and coordination can really help us achieve higher order goals. However, our insight from this experiment was that designing policies on a case-by-case scenario by hand is very cumbersome and clearly does not scale across the application, the space of possible applications. And so what we were interested in is thinking about, well, what is a more foundational approach we can take towards really devising decentralized policies that allow autonomous vehicles and machines to achieve higher order goals. And we really initially started focusing on how to devise communication strategies in order to enable this. Now, the problem of doing this is that, well, first of all, it has been shown and also proven in numerous lines of work that coordinated decision-making is a very difficult problem from a computational standpoint. Not only that, but as you go about decentralizing processes, so if you want to relax your dependency on centralized computational units, you need to think about how you're going to facilitate this. And decentralization, more often than not, requires some sort of communication. But then you have to answer the question, who are you going to communicate to, what are you going to communicate, and when are you going to communicate this in order to facilitate the performance as required. And finally, the problem is, well, more often than not, certain things in systems fail. So there is noise in the system. If you're relying on communication can be delayed or it can completely be omitted. And of course, there are faults in decentralized systems that we need to be able to deal with. And all of these things make learning through first principles approaches very complicated and complex. And so there's this juxtaposition of trying to design our strategies from the ground up through first principles, or trying to leverage data-driven approaches where we can point the systems towards these edge scenarios and let them learn by themselves. And so we're really interested in these data-driven approaches because we think they're underexplored and also because we think they're extremely promising. So the first thing that we went about to actually validate this hypothesis that learning really can provide us with valuable and effective and also powerful solutions is to solve a problem that is already solved with first principles approaches, just to validate our idea. And so we were thinking about this question of whether or not we can automatically synthesize communication strategies that lead to decentralized decision-making policies that are able to solve really difficult coordination problems. And one of the hardest coordination problems that exists is the problem of multi-agent pathfinding. So we know from prior literature and works that it is NP hard to solve the multi-agent pathfinding problem if you're searching for an optimal solution in a centralized search space. And this is why we're actually really interested in the problem. So what is our aim? So our aim here is to try to derive a local policy that can be run on an individual agent that will leverage local observations and local communication only. And we're going to try to reach or approach the performance of centralized systems as best as we can and see how good we can actually, how well we actually perform. So the system setup is very simple. We assume that agents have a local field of view, agents have start positions. They also have goal positions, but don't exactly know where these lie because our agents don't have absolute positioning. And what they're going to be able to do, in addition to seeing what's in their immediate vicinity, is they're going to be able to communicate to agents that are not too far away. So this is how we then set up the learning pipeline. We're going to assume that our system is composed of three main components. So for each robot here, we're going to be inputting a tensor that records local information. So the local information in this case would be observation of other obstacles in the area, other agents, and also goal projection. And this information is then going to be locally encoded by a convolutional neural network into some latent observation. That is then fed to a graph neural network. Now, graph neural networks are our workhorse for learning the communication strategies here, and they will emulate the communication by computing how information should be sent from agents to other agents and how that information should be interpreted on the receiving end. That output is then fed into a sequence of fully connected layers that is then fed into what we're calling our decision-making module at the very end. And that is then that then leads to the robot's motion decision, which is the result of a final softmax activation layer over a discrete set of motion primitives. So in this particular case, we're considering a grid world, so discrete actions will surface. So this is the overview of how our policy takes its shape. Now, a little bit more specifically, how do we formalize this problem? So I'm going to write down the model for this so-called graph neural network so that in my next couple of slides, I can actually convince you that the parameters that we're learning here actually lead to decentralizable policies that are actually executed fully locally on our individual agents. So here, let's assume that S is my adjacency matrix that from a centralized point of view captures how robots are able to talk to each other. So for example, if you're using a disk-based communication model, the adjacency matrix is going to be built for any given point in time based on the distances between the individual agents. So this is clearly a time-varying parameter. X then is our matrix that gathers the observations from all agents. And what my first equation here that I'm showing you tells us is how an agent I aggregates the information that is being sent over to it through a number of communication hops. And the second equation then tells us how we are parameterizing this message aggregation by right multiplying the observations with a matrix H. And matrix H here is our learnable parameter. So you can see how S and X basically are telling us how messages are being aggregated, right? Because S is our adjacency matrix, X are all the observations, and H is how we're processing these messages in order to let agents learn how to incorporate what is being sent to them. And so we can summarize this through a function G that is parameterized by θ2 that simply represents our communication function, right? And θ2 is a bank of tensors of matrices H, each one for a communication hop. So you can consider if you have a very simple communication model and you only have one hop of communication, K is equal to 1 here, and we just have one matrix H that we're trying to learn. So now that we're going to remember that we also have our CNN that is processing the observations before we pass them on to the communication module, and we also have an MLP at the end of our pipeline that is going to be feeding that into our final softmax layer. And what we're going to do is we're going to be learning these parameters in an end-to-end manner with an imitation learning setup where we're trying to minimize a cross-entropy loss function. And it's a cross-entropy loss function because you'll recall we're acting in a discrete action space with a set of 5 motion primitives. And so we can simply determine whether we're doing the right decision based on which cell the agent decided to move into. And we evaluate this cross-entropy loss by assuming that we have an expert that is providing us with the optimal actions. And because we're considering a solved problem, right? This is multi-agent pathfinding, we can actually make this assumption hold. So we know that we have solvers that can provide us with the optimal actions, and this is computationally efficient for very small systems. Now, before I talk a little bit more about how we train and solve the systems, I want to convince you that these systems are actually decentralizable. I'm going to break down this learning pipeline into an alternative view, which is the view from an agent-centric perspective. So how does this architecture present itself locally? So if we think about these local observations, which are represented by ZB here, what happens is this is our front end. So the CNN is going to be encoding this local information, and that produces a local feature vector, which here we denote by X sub B. And agent B then is going to be sharing that feature vector with its local neighborhood. Now, agent A is going to be receiving these feature vectors from all its neighboring robots. It'll also consider its own feature vector, and agent A will then aggregate that incoming information and process it. And so from the viewpoint of agent A, which is now the agent that we're considering in this pipeline, it's going to be now applying the matrices H that it learned, and these matrices H will compose our graph neural network module in this whole pipeline. And so what it simply does is for each communication hop, it's aggregating messages. These messages are then being multiplied by the parameters that it learned associated with the graph neural network, and then it will aggregate these messages or these weighted messages over all the communication hops, pass them through a nonlinearity, then feed that in through its NLP, and then activate or compute the softmax activation to compute the final decision that that robot is going to take. And so you can see here how this is fully decentralizable because every robot simply carries a copy of the matrices that were learned and processes the incoming messages through this pipeline. And so this is then how each agent acts independently, just based on its local observations and its actions. So this movie here just is to show you how our method on the right-hand side compares with the optimal expert algorithm. So I know that a lot is going on here in this movie, but what you can see qualitatively is the agents move in similar ways, and especially you can see how our system terminates at roughly the same time as the expert algorithm terminates. And this is a really good thing because it means that overall we're performing our agents are moving roughly as quickly as they would do if they had centralized information and solutions are being computed through optimal algorithms. And this is a really good thing. This is impressive not only because we're doing this through a learning-based solution, but also because our solution is acting upon much less information, albeit leveraging communication. And so that's really the elegance of this system. And so this here is then also evaluated quantitatively, where we show how we have very high success rate for systems as we scale them to larger systems, and we perform much, much better than alternative, discrete, decentralized versions, which would be acting upon the same amount of information as we are. Okay? So now you're asking the question, well, do we always need decentralized solvers? And if we do, how does a learning-based solution even help us? Because we always need decentralized-based solvers to act as our experts. Well, here comes in the question of generalization. And obviously, if we leverage the solution we devised before, and we start scaling to systems that are maybe 100 times bigger in scale, it tends to perform a little bit less well. And so we thought about what do we need to do in order to maintain performance as we scale to really large systems, so systems that then can no longer be solved through the same centralized solutions because they're just computationally intractable. And so our idea here was, and this is one of many possible approaches, so our idea was to say, well, we're going to be leveraging attention, because as we scale our systems, we potentially have more and more information. And so our robots need to learn what messages we need to pay attention to in order to really compute effectively and which paths we're going to take in order to still be solving our systems effectively and efficiently. And so we are, in addition to learning our parameters H here, which belong to the communication model, we're going to be learning an additional matrix E here, which is simply being multiplied through a Hadamard product with our adjacency matrix. And this matrix E here is simply learning attention. So it's learning what messages are actually relevant to the robots to be able to perform optimally. And so we then deployed the system, and as you can see here in the results, success rate for MAGAT, which are the blues and greens here, is much, much higher as we scale our systems than for the vanilla-based, GNN-based system that I presented to you before. And what's really interesting is that we're maintaining really high success rates as we scale our system to 100 orders of magnitude larger than those instances that we're being trained on. And just to give you a little bit of a feeling of why this is so relevant, for systems of, say, 40 agents already, using solvers such as CBS, which was our expert in order to train these systems, already time out as we approach our limit of 10 minutes for solving a system of 40 agents. And that's why it's so relevant that we can then scale our learning-based decentralized solutions to 10 or 100 times larger in size, because these are tractable given the speed of the policy inference and also the fact that we're running them on decentralized systems. So I showed you a little bit of the things that we can do for learning communication, but we actually also took a different stance and said, well, is communication really the only way about solving hard coordination problems? And it turns out that there are some scenarios where we can actually get around using communication. And so this problem here, we decided we'd use reinforcement learning to show that agents can learn to effectively and very efficiently navigate in very complex and dynamic environments just by observing what's happening around them. Now, the problem of using reinforcement learning in complex multi-agent settings is that we don't really know how to devise an effective reward signal for the robot to A, avoid all other robots in its vicinity effectively, not get into any live locks or deadlocks, and still achieve or reach their final goal destinations on near optimal paths. And so the interesting thing that we came up here with was an idea of how to densify the reward function through what we're calling a thing that is called global guidance. And so the idea here was to say, well, we're going to give our agents a reward that basically allows them to not run. So the reward gives the robots a small positive reward for not running into any other robot and not running into any obstacles. But it also gives the robots a reward for re-reaching the globally optimal path. So if you look at this little example that I'm showing you in the bottom, if the robot needs to deviate from the globally optimal path because it has to avoid an obstacle or avoid an oncoming agent that is moving in its vicinity, as soon as it finishes its deviation and rejoins the gray path, it will reap the rewards of the whole gray path as if it had traveled on this optimal gray path since the beginning. So we're trying to not penalize the robots for avoiding other agents that happen to come into their paths during training time. And this turns out to be incredibly effective because the robots learn to deviate other robots minimally whilst achieving paths that are really near optimal. And so I realize I'm coming up to close to 20 minutes, which is the end of my talk. So I just want to show you one last thing that we did that we're really excited about before concluding the talk. And so I'm going to skip the results here because you can look them up in the paper in the interest of time, and move to the very last thing that I wanted to point out here, which is as we're looking at these environments that are very complicated, and I showed you several environments where we have multiple agents interacting with each other in cluttered environments, cluttered grid worlds, think road environments, city environments, or even warehouse environments. Another thing comes up, which is the role of actually having rules in these environments. I'm going to talk about this in the one final step of simplification. So we went from multi-agent with communication to multi-agent without communication, and now we're going to take this system a little. We're going to take it back even more and simplify it one more level. We'll say we're actually going to think about single-agent systems, but we're going to consider the full complexity of the environment. What we're going to be saying here is that, well, actually, if we're having our agents move in environments for which we know there are certain rules that exist, and we want the agents to abide by these rules, well, it is valuable for these agents to collect diverse experiences with regards to these rules. And if they are able to collect experiences and learn from these experiences in a way that prioritizes experiences across the diversity of these rule sets, this will lead to the agents behaving with policies or learning policies in a much quicker and more efficient way than if these experiences have been sampled or collected in an agnostic way with respect to the underlying rule sets. So what exactly do I mean by that? So I will exemplify this through two environments that I'm going to talk about a little bit more in detail. So we consider this in both discrete and continuous worlds, where we're saying, well, simply what we want our agents to do is to learn to drive on roads and to drive as long as possible without infracting speed limitations. Now, the interesting thing here is that in both of these environments, the speed limitations are going to be set by the type of the road. And the types of the road is going to be a function of multiple properties of the road environment, maybe also the agent's properties. So there are going to be several properties that culminate together in combinations that set the road type, and the road type then sets the speed limits. And so the agents have to learn to infer how to not go over their speeds as a function of underlying road types. Now, we're going to be running these tests in environments of different complexity, so easy, medium, and hard, where the easy environments have just a few properties, medium environments have maybe a dozen properties, and hard environments have more than a dozen properties that the agents have to learn to infer from. And our reward structure is going to be very, very simple. So agents simply get penalized for speed penalties, they get penalized for off-road driving, and they get rewarded if they cover new roads. So their incentive is really to cover the whole drivable environment. So what do we do? So our idea is actually really simple. And what we're going to do is say, well, we're going to be trying to learn the meaning of agent actions by associating them to experienced consequences. And our approach is going to be to modify conventional prioritized experience replay methods within reinforcement learning by generating clusters. And these clusters are actually going to represent explanations that we imbue on the experiences made by the agents. And every single cluster is going to be associated with a distinct explanation type. And then instead of sampling through classical prioritized experience replay, we're going to be sampling according to the clusterizations that we did. And so what we're saying here is actually this is a paradigm shift from instead of thinking hard about shaping the rewards of our agents in complicated environments, we're just going to say, well, we assume that we have some sort of way of labeling experiences through explainers, and then we're going to let this clustering strategy do the rest of the job for us. And so just to wrap up with a couple of results here, we added our modified cluster-based experience replay on top of existing standard seminal reinforcement learning algorithms, both in the discrete domain as well as in the continuous domain. And so what I'm showing you here is actually a snapshot of some of the results we present in our paper. And what you can see here, so I'm highlighting the bold results that are those that perform best, is that for both the discrete, that is the top half of the results, as well as for the continuous world, which is the bottom half here, the best performing environments are actually the ones that leveraged explanation-aware ways of sampling the experiences that the agents made. And we actually outperform the baseline algorithms, so TD3 and DQN, significantly when we leverage explanations in the learning process. And what's also interesting is that as our environments get harder, the more our agents are actually really able to benefit from the explanations during the learning process. So apologies for this tour de force through the various things that we're working on within the lab. I just want to end with a couple of take-home messages here. So the first thing I'd really like to stress is that GNNs really facilitate the learning of distributed policies and the importance of doing this for multi-robot systems. This really also provides us scalability at very little performance cost. And finally, I talked about explanations being really key to the learning process, especially if we're acting with our agents in environments that are human-centric and imbued with many human-devised rules. Many things that I'm excited about beyond explainability, sim to real, obviously talking about performance in the real world, fairness across multi-agent coordination, and also resilience, which goes beyond just developing robust policies for performance in scenarios where consequences might be unknown. I'd like to thank my students and collaborators who contributed to this work, my reviewers, supporters, and also funders. And of course, thank you so much for your attention. Apologies for going a little bit over time. Thank you.
Thank you very much, Professor Amanda. Do we have any questions?
Thank you very much, Professor Amanda. I had a question on the scalability aspect of the algorithm. Now it's decentralized, and I understand, from what I understand, the way to reduce the load on the agent is by having the attention matrix E. But that still means all the messages are cascaded down all the agents. What if you scale up the system exponentially? Would that still mean all the messages have to be transferred across all the agents, or there's a smart way to relay the messages from one agent to another?
Thank you so much for the question. That's great. So we actually don't assume at all that we have information coming in from the full system. What is key is, you can assume any given communication topology on the system, any given communication model on this system. So if you want a fully decentralized system that is, say, limited to one-hop communications at runtime, this policy will function with one-hop communications at runtime. So if I have a 1 meter communication radius, I will only be able to talk to robots or agents that are within a one meter distance to me. And I don't at all assume at any given point in time that I'm getting messages cascading through from agents that are farther away than that. What is important to note here is that during training time, what the agents see is should in an ideal scenario, be similar to the conditions they will encounter at test time. So if during training time, whilst agents are moving around, they should, if you know that during test time you only have a 1 meter communication range, during training, that is how the communication should be run, ideally, because the patterns, the communication strategies that they learn otherwise do not correspond to the policies that they would be then running at runtime. But there's no assumption that messages have to cascade through from agents farther away than 1 meter if that is what your constraint is. Does that answer your question?
Largely, yes.
Okay.
I'm just thinking, is there a risk of overloading the message channel on an agent? And would there be a smart way to, let's say, cluster the messages spatially to say that agent to the right will receive it with a certain key and they will ignore messages that are traveling to the left, for example?
Yeah, I see your point. So that's, I would argue that's almost more a communication engineering question, in the sense that if in the real world at test time you actually have a system that has a very large communication range and you're running a lot of robots, then essentially the density of your multi-robot system will play a major role here, because you're going to be receiving a lot of information, and it's going to be essentially communication channels going to be cluttered. And I don't want to give away too much, but we are actually working a little bit on the systems engineering side of things to alleviate bandwidth issues and contention issues that arise in exactly those kinds of scenarios. But clearly, the algorithmic side here, we don't think that would be able to help much in those scenarios. It has to be approached more from the systems, the physical side of things. Thank you.